So in this talk, basically, I'm going to give you an overview of the field of knowledge dynamics, which is a field in symbolic AI that studies how you maintain and evolve a corpus of knowledge. And here, I'm going to give a brief overview, and then I'm going to focus on a research line that basically what we follow is that taking knowledge dynamic from classic logics and going towards non-classical logics that are basically most of the logics that you use nowadays to represent and reason in AI application. And then I'm going to talk what's the challenge there. And when you go to these logics, sometimes you need to resort to infinite structures. So the reasoning in these logics has some infinite elements that complicates things there. So basically, knowledge dynamics, it's the name of the field, but it's also the process of modifying a body of knowledge, right? And you humans usually do that in an easy way, or at least it seems easy to do. So for instance, you open your mobile or your laptop and then you get some news. So things happens in the last days and then you start to modify your beliefs or your plans. So have a trip schedule, or to have some flight cancellations or your trains delay, or have some cancellation, you need to review your plans, your beliefs. You get to the destination, you need to rebook things, you need to get another plane to get to the airport or another thing. So you do that every day, right? Weather changes. But science is also intrinsically connected to modify knowledge, right? So have some model that explains something, but over time you do other findings and then you refine that knowledge. So you believe that the human body works in a way, then later you get more knowledge and you discover that works slightly different. You prescribe the medicaments, the medicine, and then you learn better about that, and then you change the treatment protocols. But imagine that if you're doing AI applications and other applications that resort to this kind of knowledge, your application should be able to cope with these changes so you can keep giving accurate decisions, support accurate decisions in these applications. So if you want to assist some diagnosis or treatment in the medical scenario, we should be able to get this new information about science and about medicaments and the human body, the treatments, right? So we should be able to develop applications that change the knowledge as it's needed. And there are several other applications that I could cite here, but here I'm going to focus in one of the applications which we are interested with my co-author, Dominic Klum. That's basically how you can repair systems. So imagine that you have a system, and of course you want this system to work correctly according to some specification that you have some behaviors that must be followed. But when develop these systems, sometimes you find out that there's a mistake, and then you need to modify that system to satisfy those specifications, those requirements. To keep this small, and then you can understand basically the idea, I put here a very small example, the model of a system from a server, and basically what it does, it can receive some requests, do some processing, and eventually it reply to those requests, right? So in the initial state, it is idle, you have no request, but also it does nothing. Then when it gets a request, it starts processing and go to the state where it's doing the processing. And then later it replies, but during the reply, it might receive something else as input, like another request, right? And for the server is basically handling requests and reply, a natural behavior, a natural requirement that you want that every request is eventually replied, right? So basically, you can formally represent these in some logics like LTL. So here I'm anticipated a bit, and I specify these using the linear temporal logic. It basically says that in every time, in every state of your system, if you receive a request, somewhere in the future you need to reply to the request, right? If you look closely to the system, however, this system does not satisfy the specification. So just let me show you an execution that fails this. So basically, it's initially here in this state, then it gets a request and starts processing this part here. Then when it's going to reply, it receives another request. But the second request is not replied because it goes to the idle states and say here forever. So the second the second request is never replied. So you need to do some changes here. So you need to modify the system so the specification is satisfied. It might not be very clear. Maybe you need a bit more time to check this. But if we put this loop here and you change this transition here to forbid request, so when you go back, it doesn't receive a request. This specification will be satisfied. So basically, the idea here is that you have a specification, that's some information that you want to be satisfied, and you modify your system. And the problem of preparing the system can actually be seen as a knowledge dynamic phenomena. So if you look at this model, you can understand that the model that you have here is the knowledge, represent the knowledge that you have about the system. So every property that you have from the system here, if you look to the model, it corresponds to what you know about the system. And then you have here some specification and other information and the knowledge. So your model needs to comply to this information. So basically have new information, you need to accommodate this new information, this body of knowledge. But it conflicts with this, it does not satisfy. So you need to modify the body of knowledge which corresponds to modify the system of the model. So basically you can see system repair from the lens of knowledge dynamics. It behaves as a process of modifying knowledge. If you can look from these, then you can use the strategies for knowledge dynamic to support the automatic repair of systems. So this is basically one of the research questions that you are following this time. But these systems, you need more intricate logics like linear temporal logics, as I showed here, is not these classical logics. So knowledge dynamics basically investigate this process of modifying a body of knowledge or several body of knowledge. So imagine that you have a different knowledge base, like you have some specialized knowledge about the human body, about medicaments, and then you want to combine them. So you modify knowledge there, want everything to be consistent, how you do this. So basically knowledge dynamics study this process of modifying corpora of knowledge. And there are several dimensions here. So a lot of things are related to that. So for example, what kind of information you addressing here? It is static or dynamic environment. So basically, maybe nothing is changing in the environment that you are. You just got an announcement. You just got some new information. You open the news and you revise your beliefs about that. So exactly, you didn't change anything in your room or where you are, but you just become aware about some information that you did not know before. So an environment, it's static. But maybe you might need to handle these different if you are in a dynamic environment. So have more than one robot that are doing some tasks in the room, but the action of one robot might interfere with the action of the other robot, and they can interfere with the goal of another. So each one of them has a plan, but the action of one interferes with the plan of another, and they need to respond to that changes on time. So how the knowledge that each one have about that, and if the changes, how you replan those actions. So you need to address that in another way. Knowledge dynamic is also related with epistemic, those are logic with the dynamic layer on top of that. So usually in epistemic and those are logics, we're more interested in what you know that someone else knows that you know. So I have a collection of agents, what one agent knows about the other. But we have some announcement, more important now that I have new information, what I know that the others know. So basically you can specify what you know in the language of epistemic, those are logic. And these dynamic operators is reasoning about the dynamics correspond to this knowledge dynamic phenomena. We can also reason about that. So basically knowledge dynamics have some principles about how this works, and you try to embed these principles inside the object language of these logics, for instance. So maybe interest on that as well. Another thing is the form or the kinds of changes. So what you interest here, what's happening? You gain information, you're removing information, so you're deleting deprecated knowledge, or maybe receiving some set of information, and then you do some value judgment. So not everything that you're receiving is plausible. So you might believe that something is true that you receive, but the others is not so credible. Maybe I do not believe much in that source, or because some information that came together since one of them is to contradict the other or be an argument or hinting towards some lie that you got. So you might not want to accept everything. So how you do this selection, what's the impact of that in constructing this new body of knowledge of handling those changes. So there are a lot of dimensions here when you're addressing the phenomenon of knowledge dynamics that you need to address. You need the proper frameworks to guide you on how to do that. Another thing is knowledge dynamic is tightly connected to machine learning frameworks. So in the learning frameworks, usually what you have is like you have a task, but usually you don't have the complete definition of this task. You don't have access to that, the task or the concept or the function that you want to learn, but usually you have some observation about the task or some behavior, some data. So you get this stream of observation of data. And from those observations, try to learn a model, to construct a model that approximate to the task that you don't know exactly what they are. So basically, you're going receiving observations, and then you're going refining that model towards the object that you want to learn. If you look from this perspective, you can see that it's very tightly connected to knowledge dynamics. So basically, knowledge dynamics have initial hypothesis, initial belief. Then you start to get new observations, then you're going to minimally modify your knowledge so it complies with the new stream of data iteratively in each step. So from this perspective, you can see the knowledge dynamic has some similarity of the learning framework. So after you receive this stream of data, your hypothesis, your new knowledge of body correspond to the approximation of the task that you want to construct, that you want to learn. And there are works towards this study, the connection between knowledge dynamic and learning frameworks. These are several dimensions that I talked to you that I'm interested and you are conducting. So for instance, in the connection with learning frameworks and knowledge dynamic, we also studying that with other co-authors. And for instance, with Anna Ozaki, you have started investigating the connection of knowledge dynamics with the framework of learning from interpretation in classes of description logic, and have some initial results there. And in this year, you got an outstanding paper award for those results on that connection. So there are several dimensions here about knowledge dynamics. I gave an overview for you, but unfortunately, I won't be able to get in details of everything. But please feel free to discuss that if you want after the talk, or send me an email or everything. I'm very open to talk. But for this talk here, I'm gonna focus on a specific dimension about knowledge dynamics. That is basically the effort of taking knowledge dynamics to the set of non-classical logics, with basically logics which are used for these more intricate knowledge that use in AI applications in computer science, like specifying the behavior of the systems, the requirements of your systems, the linear temporal logics, or the formal verification system, for instance. So basically, I want to talk about this trajectory of going from classical system to non-classical system, the results that you got, and the challenge involved on that. As you can see, that the field is huge. There are a lot of dimensions that you need to consider. On this path here for the talk, I'm going to talk about the AGN framework for knowledge dynamics. That's basically the central pillar of the area. So basically, most of the other strategies and framework to do with knowledge dynamic in the fields are built upon this AGM framework. It's essential in the area. So basically, if you want to take knowledge dynamic to this non-classical system, this more intricate system, the natural path is first for you to extend the pillar for these more intricate systems, so you can construct the rest on top of that. So this is basically what you're doing here. I'm going to focus on the constructions and towards the end more to the computational aspects related to this. So I talked a lot, but I think I didn't give an example highlighting exactly how knowledge dynamic could work, right? So I put here a small example just to illustrate a bit in a medical domain. So imagine that I have a medical ontology specialized knowledge about the human body and medical information. And it says that pneumonia is a lung infection. We know that pneumonia is treated with first-line antibiotics. And first-line antibiotic, they are basically penicillin-based. So basically treating the patient with penicillin. You have the information, the doctor has the information that the patient has pneumonia. So if you put this together, you conclude, okay, I'm going to prescribe a treatment with first-line antibiotics, that is penicillin. But then when the doctor is checking on the history of the patient, he sees that he has allergy to penicillin, so you cannot prescribe the treatment anymore. So you need to change something here on your rule. Of course, you want to avoid here some spurious change, right? You could remove everything and just get with the input that patient has allergy to penicillin. You do not want that. Information is valuable. There are some information that are more reliable than others. So it would make sense to relax the rule 5, patient with the second rule, pneumonia is treated first-line antibiotics. Maybe you want to relax these. Want to do that unless the patient shows some contraindication, or maybe you can relax first-line antibiotics and another family of antibiotics. But it doesn't make sense to remove that pneumonia is a lung infection, for instance. So the question here is what you modify, what you do not modify, and basically want to keep most of the original information, modify only what contributes to the conflict of your new information, right? So what changes you do here? So basically we learned some principles to guide you. So basically you can see knowledge dynamics or belief dynamics as well, is also called, as a process of modifying knowledge, a body of knowledge, into a new body of knowledge when you're confronted with some piece of information. And you want to do this guided by some principles, like some minimal change criteria here. In the field, basically, this principle of minimal change are conceptualized via rationality postulates that tell us what is rational, so give us guidelines to tell us what is a good behavior to modify your knowledge. These tell us a what, but we have to perform belief, this knowledge change. What you want is the operator. You want to know how to perform these changes, right? So basically, you have classes of operators that satisfy these rationality postulates, exclusively to tell us how to operate, how to perform. And also what is nice is that these classes, they are complete. So basically, any operator that you try to define that satisfies the rationality postulates fall in these classes that were defined. So the perspective of what is rational and how to construct a rational operators are tightly connected. You know what is plausible and how to construct that plausibility, that rational operators. We call this a representation theorem, right? And since you want to deal with reasoning and support decisions, this body of knowledge, they are specifying some underlying logic, some suitable underlying logic to the domain that you want to specify. Could be classical propositional logic, first-order logic, depends on the domain that you want. And these principles, I'm going to explain, they are general enough to comply with these logics, but I'm going to open that very soon. So basically, you want to represent knowledge, but you also to support reasoning, also to provide some explanation from that decision. So that's why you use logic. So have the reasoning operator. But here, I'm not going to focus exactly in one logic or two logics on how these logics are defined. Usually address these in a very high-level perspective. So I want to know what properties you need so you can support these knowledge dynamics operators and these principles. So a logic here is treated just as a pair, the language. So how we specify your information. So logic prescribes some syntax to specify that. And a consequence operator that basically from a set of information you might draw some conclusion. So this is what this consequence operator does, but you're not interested in how you define this consequence operator, or usually much about the syntax of your logic, of your language. You might do some assumptions, but you're not so interested in the details of this. It's very general, a language to specify your knowledge and a consequence operator to draw conclusions. And if you want to do knowledge dynamics, you just need to know some properties about this logic. Otherwise, you have almost nothing here to help you to guide. So here I'm going to look for the standard assumptions. And unfortunately, in the standard framework, you have a lot of assumptions. So the logic has to be Boolean, the language has to be Boolean. So you only require the classical Boolean operators. You can have others, but you need the Boolean operators. And the consequence operator needs to satisfy some properties, like it needs to be Tasking, compact, deduction, satisfy superclassicality. I'm not going to list all of them, but only those are really important here for the talk, which are the logic to be Taskian. So this means that you need to satisfy 3 properties. Monotonicity, which says that if you gain more explicit information, you do not lose entailments. So if you gain more things, you do not lose things that you entail. Inclusion say that you do not lose explicit information. So if you believe in alpha, you still entail alpha. You don't lose explicit things. And idempotent only says that this consequence operator is actually a closure operator. So you get everything that you believe, everything that's entailed. If apply again, you do not entail anything else because it's closed under the entailment. So this is what being Tasking means. And compactness is a property that says that if you entail something from a set of information, you're capable of entailing that from a finite subset of that. So you only need finitely many observations to draw any conclusion. It makes sense for classical logics, but you go for temporal logics like LTL, for the example of the system repair, they do not have compactness because you need to reason with time, and usually this time it unfolds infinitely to the future. So you do not have compactness, for instance. But then what logics are covered by these classical assumptions? There are a lot of them, actually. Classical propositional logic, first order logic, fragments of first order logic, like the monadic fragment and some others. So there are some assumptions, but they're still useful. But if you look for more of the applications that use today knowledge representation reasoning, you need more intricate logics for that job. So basically, you want to use description logics for semantic web and medical ontologies like YAL, YAL++, ALC, and some others. There are several of them in description logics. So here are an example, some excerpt from the ISNOMED medical ontology. It specifies an EL++, which doesn't have negation. So it's not Boolean, for instance. So it's not covered by those assumptions. But once you represent and reason about that, knowledge changes as you explained, how you do knowledge dynamic in these logics. If you go to temporal logics for form specification and verification of system, LTL, CTL, calculus, and other logics that are also used, for instance, in AI for planning, reasoning about actions, you need to use these temporal logics, for instance, but they do not have the compactness properties as I told. So you're not covered by those assumptions. The question now is, you want to deal with knowledge dynamics, you want those principles and you want to know how to operate, but that representation theorem that connects them depends on the classical assumptions. The first question is, you really need those assumptions or not? Okay, if you do that questions and you did that and you look carefully, if you remove compactness or Boolean, this breaks down. So basically, if you want to use those minimal change principles, you don't know anymore how to operate. So the question is, why this breakdown and how you can move on to these more intricate classes of systems. And this is what I hope to give here a perspective on this talk. So basically, I wanted to highlight where this breakdowns and how you can move on in that path to be able to support knowledge dynamics in these more expressive, intricate systems and logics. So what I do, I'm gonna open this box a bit in a very high level perspective. So I'm gonna visit those standard constructions, and from that, try to see why this breakdown and how you construct new classes of operator with these more expressive logics. Here, I'm going to focus on the second part that are the temporal logics, and I'm going to discuss much on the non-Boolean because I'm not going to have time for that, but we'll have that worked on that as well. So I focus on the non-compactness part. But first, we go into the standard framework of knowledge dynamic, which I told you in the beginning that was the AGM paradigm. So in the AGM paradigm, which is the name is due to the initials of the original authors, Auschwitz, Gardenford, and Maxon. And you distinguish three types of operation. Expansion, that's basically you just gain the information, have the information put in your knowledge base. Trivial, not very important about that. But the two other ones are more interesting, which are contraction. That's when you want to remove, you want to relinquish some obsolete information. You want to remove that from knowledge base. That's not true anymore. The third one is revision, where you want to accommodate the new information, but you want to guarantee that you're going to remove any inconsistency. You want to guarantee that the new knowledge base is consistent. There are no conflict there. So you want the information that the patient is allergic to penicillin, but you do not want to prescribe a penicillin-based treatment for pneumonia. That's going to endanger the health of the patient. So you want to do a revision for that, right? So you need to accommodate something, but you need to drop something. Here, I'm going to focus on contraction, and the choice of that is because contraction is central. If you think about minimal change, for instance, you can think that to accommodate the new information, you want to remove as little information as possible, only information that contributes to the conflict, so you can accommodate the new information. And then, so you can understand this principle of minimal change much better from the lens of contraction. Contraction is also the main ground for the other forms of belief, of knowledge dynamic operators like revision. If you want to get a new information alpha in the knowledge base, you can contract any conflict. So you can contract not alpha. Then you don't have any conflict anymore. You do that minimally, guided with some principles. Then you save to accommodate alpha. So you don't have any conflicts anymore. So if you serve contraction, you can basically transpose these, project these to construct the other forms of belief change. That's why I'm going to focus here on contraction. But you can achieve revision from this, okay? So I compile here some of the postulates, but I'm not going to get into the mathematical definition. Just want to show you they exist, they're plausible, there are ways to properly define these principles. But I want to focus on the idea of what you can construct from that. Also, usually split them in the basic ones and the supplementary ones. So the supplementary ones are more related to how you sort your knowledge. So they are information, they're more reliable than others, and there are proper ways of doing that to guarantee this rationality. So not every choice is rational. You need some sorting there. The most central construction in the standard construction of knowledge dynamic in the AGM is known as partial meet, which basically uses a select and intersect strategy. So basically, if you want to construct a formula alpha, you're going to look at remainder, which is basically a maximally preserving subset that does not entail the formula alpha that you want to contract. You might have more than one remainder, but you might be unable to tie break that. It looks all plausible. If you cannot tie break, you choose those that looks the best ones, then you intersect. We stay with this common to your best options. So just to make it clear, a remainder is a subset of a knowledge base K. I let the circle here, where I'm depicting in a high level the knowledge base of alpha that you want to drop. So the remainder is a subset that does not entail alpha, but it's maximally preserving, which means that any information phi that you removed was because phi contributes to entail alpha. So you put any of these formulae phi that were removed, if you put back alpha, you restore. But what is nice in this standard framework is that because of those extra assumptions, these remainders as a side effect doesn't mean that you get only alpha, but you get everything back. So it's really maximally preserving. We focus on the connection with alpha, but it says that everything else is also restored. But this is because of the other assumptions. So here's the proper definition of the remainder. As I told you, is a subset, is not entailed, but you put anything that was removed, you removed because it contributes to alpha, and I explained the side effect of restoring everything. And here's the standard notation for the set of all remainders, because you can have more than one. And if you have more than one, then you're going to choose some of them, the most plausible ones. So for now, just imagine to have a choice function that realize this choice. And what you do, you intersect them. And this is the result of your contraction, a very high level intuition, right? But of course, these choices, they are not arbitrary. They're based usually some preference relation. There's some information that are more reliable, they're more plausible than others. Then when you are contracting, of course, you have preference to keep those that rely the most. You can rank, you can classify information direct, but as reminders contain the information, you can also rank, you can classify your preference between the reminders itself directly. So basically what you do in the area is you assume a preference relation between the information or the reminders in this case, and when you want to contract, you choose the best ones, the ones in blue, for instance, and then you do the intersection. But this preference relation, they need to satisfy some properties. Okay, you can complicate a bit more. But in this level here, to connect with those supplementary ones, everything, the standard way is just to assume totality. So totality suffices to do the contractions. If your choice function is based on a total preference relation between the reminders, you're gonna guarantee full rationality. So the partial meet alone connect with the basic ones. If you saw these with those preference relations, you have full rationality, you have basic and supplementary ones. So you can connect with that, but these relies on those classical assumptions. So the idea here is what happens if you want to use those temporal logics that do not have compactness? As I told you, that connection breaks down. Questions, what I do from here. What is the role of compactness on this? Why you need compactness at first place? So this is the first question that you posed. And what you found out is actually, okay, what happens? Without compactness, you do not guarantee the existence of reminders. But the question is reminders really connected with those rationality postulates or not? What's the role of compactness on this? What you showed actually is that compactness only facilitates the definition of those operators. It makes it easier to find how they behave, but you do not need reminders. That's another way to do that. Reminders is just that to facilitate. But if assuming compactness is only facilitate things, do you really need the other assumptions or not? You want to go to this more expressive logic. So which assumptions you need, which ones you don't need, so you can start moving ahead for this more intricate system. So here you pose this question, and then what you found out is if you want to dispense with compactness, you only need the logic to be Boolean and tasking. You don't need anything else. So you don't have all those assumptions. You only need the logic to be Boolean and tasking. If you want to go to logics that are not Boolean, then another way of solving this is another set of results. But here I'm going to focus on the path of dispensing with compactness. You only need this. Okay. And the problem is that remainders are internal structures of your knowledge base. If you want to go ahead without compactness like linear temporal logics, what you found out is that you can use some external structure for your knowledge base. So instead of maximally preserving subset, you look for complete consistent theories that are maximal subsets that are maximally consistent. They are sets of sentences that are maximally consistent. So you take a set of sentences, and everything that you leave behind are information that conflicts with that set. So you take any formula phi that's outside a complete consistent theory, if you put that back, it is the whole language, right? So it conflicts with what you have. And now instead of contracting, intersecting reminders, you're gonna intersect complete consistent theories. So you're gonna choose complete consistent theories and you're going to intersect them. So you're gonna do that choice and then intersect them. And what's interesting now is that it's much easier to define a revision using complete consistent theories. You don't even need to resort directly to contraction and go directly for complete consistent theories. What's the trick? For contraction, since you want to remove a formula alpha, you're gonna choose the best complete consistent theories that do not have alpha, because you want to remove. For revision, you're gonna choose the ones that contain alpha, and then you intersect. For revision, you only need to intersect with your choice when you do the revision. For contraction, you need to save a subset, you just want to remove information, so you intersect the back to scale. and then you have your result. Then you can do a contraction. Of course, these choices need to be sorted somehow. Totality, however, does not suffice to get full rationality. So not every contraction can be defined in terms of totality in the preference relation. So totality is too restrictive here. So you need to relax this. You need this to have more expressivity. Also, totality is criticized because it's too demanding. So sometimes the information that does not make sense to compare them. And totality forces you to compare. So for instance, if you have the concept knee surgery and show the surgery, why you want to compare them? If you need to prescribe a surgery for the patient in the knee or in the surgery, that's no preference, they're totally unrelated parts of the body. Or you need a knee surgery, you need a shoulder surgery, you cannot have a preference between them. It doesn't make much sense. Totality tell us that you need to rank these, but you don't need. The idea here was to relax this totality with mirroring that says like, you can have concepts, elements that you do not compare, but if you make one more preferable than one, then you need to mimic the other one. So show that any surgery are uncomparable, but I might find it plausible to prescribe first a painkiller treatment before going to surgery. That makes sense with this preference to be mimicked by the two concepts. So you can relax totality with mirroring. And if your preference relations are specified with mirroring, instead of totality, then you restore that representation theorem between the knowledge base, between the rationality postulates and these new kind of constructions. Also having revision a more direct way to construct. So the next question is, now you reconnect these with what and how. The next question, how can you compute these operators in these logics? This is another challenge, right? And this is the question that you pose. So for instance, if you want to give support for system model repair, then you want to implement those revision and contraction function in linear temporal logic, for instance. So your system is wrong with the information. You have the knowledge of your system specified in your logic. So this is a representation of all those properties that satisfy but your system. Then you need to modify that knowledge with the new information. Now I want you to walk towards implementing this. You're not there yet, but this is where you want to get. So basically what you do here, you start looking at this, but not only with logics without compactness is another class of logics. So those other ones, even those classic ones, what you found out is going to suffer with uncomputability. I'm going to explain what it means. And you look this for non-finitary logic with some conditions that are basically logics where you can specify infinitely many formulae, different formulae, not logically equivalent formulae. Usually in the area of knowledge representation, and we have some problem with time complexity, like it's too expensive, or some computability problems. What you do usually to constrain the syntax of the language of your logic, so you do not let it specify everything. You remove negation or some other thing, or you restrict how these operators can be combined, and then you contain complexity or computability, for instance. Or you can restrict the space of what you want to represent. So like the set of sentences that you want to represent. What to show is that it doesn't matter how you try to constrain, as long as this is non-finitary and computability will remain. It means that there will exist AGM contraction functions that cannot be computable, cannot compute. The question is, can you identify which class of AGM contraction functions can be computed, so you can move towards the application. And to show that this is very difficult because these standard strategies do not work very well. You need a different perspective to address this if you want to distinguish the computable one versus the not computable ones. You give this result in a very high level. We're going to discuss about that. And to be able to distinguish between computable and non-computable ones, you look at linear temporal logics and use Boole automata to represent and reason with knowledge in linear temporal logics, and Boole automata to specify those preference relations and identify a class of functions that can be computed. So basically here you go back to those assumptions. So basically you're gonna make some assumptions about the language and some assumptions about the consequence operators. So it's Boolean and Taskian. But now you're gonna focus on languages that are non-finitary. So basically if you take your language and you break into equivalent classes, you have infinitely many ones. The finitary one is trivial because you only have finitely many information, so this can be computed. So that's the easy case. So you're looking for the hard cases, the non-finitary. And the surname is appropriate from possible word semantics. I do not want to enter the definition here, but it's just some conditions that you need for this. And it's still broad enough. So those logics that you discussed, they're still covered by these assumptions. Here. What you showed is that it doesn't matter how you constrain your space of the epistemic states are the set of knowledge body of knowledge that you can represent with your logic. It doesn't matter how much you constrain that, it's still going to exist AGM contractions that cannot be computed. The question is how you can identify classes of contraction functions, therefore you can move to revision that are computable. Can you distinguish them? Can you obtain them by design? What we did was to look at LTL and use Boole automata. It's a class of automata that recognize infinite traces to represent as an intermediate structure, to represent knowledge in LTL. So all those body of knowledge will be represented by Boole automata. And you can do reasoning with these structures. And then those knowledge dynamic operators like contraction will boil down to do some operations between these structures to get to the final body of knowledge. So that's basically the main strategy. And if these want to move from that theoretical framework towards the applications using these logics, as we discussed in the beginning. So basically you have a body of knowledge K, you have an information alpha that you want to drop in, want to generate the new body of knowledge. So basically what you're gonna do, K is gonna be represented by a Boole automata. You're gonna generate a new Boole automata, AK prime, that's the result. And if you remember, the idea is that you're gonna choose some complete consistent theories that do not have alpha, with equivalent to have not alpha in that. But this choice function here, since you want to represent as a result of Boole automata, the choices that you have is you need to be represented by another Boole automata. So all those CCTs need to give an epistemic state which correspond to the selection of your complete consistent theories, which is not easy because not every set can be expressed by a Boole automata. So you need to take care of that. And another thing is that computability, it's reduced to guarantee the computation of this choice function. So if you can compute this choice function, give your preference relation, then these would be computed. And this is exactly the class of computable functions if you're using Boole automata. So I have another representation theorem here. But how you can guarantee these two conditions that your choice is going to be represented by a Boole automata, that this is computable, and also that you can represent those preference relations. So the idea is to use Boole automata that transduces to represent those preference relations. So the Boole automata, you recognize pairs instead of just pair of traces instead of just one traces. And then if you recognize pairs of traces, then you put preference relation between these pairs. And then you can look at what the best traces given a formula alpha. This is guaranteed to be represented by a Boole automaton. I'm going to show that. And you guarantee that the best ones, you can find them, and this is computable. There are a series of operations that you can apply, and then you get your final result there. So this can be computed. Now, this is an example of a Boole automata. So you can see that it's recognizing pairs in the transitions, and then this means that you recognize a pair of traces. So you say that the traces pi 2 is better than pi 1 by these traces. And here you have a Boole automata about a knowledge about prescriptions. Okay, so it says that you prescribe some pills for a patient, but in this treatment, if the patient take a pill today, he cannot take the pill tomorrow. You should alternate taking these pills. But now the patient need a higher dose, so you're gonna need to take 2 pills appeal 2 days in a row, and then later it go back to alternate if it's needed. So you cannot stay with this knowledge anymore. You need to update this. So what we do, you want to remove that. You want to go to the next one. So you want something that has 2 pills in a row, and then later anything it's okay. Come back to the previous treatment. You have the preference relations on how you prescribe these pills for the patients. And then you want to do the modification. So basically you want the best CCTs or the best traces that complies with the first automata, with the first knowledge, because you want to drop that. As I told you, that's a way to find the best elements of any Buchimili automaton that's specified by the preference relation if you give the set of all formally phi there. So you find the best ones that you want to maintain. That's this one here. Now I'm gonna get in details of the operator. That you do a series of operations going transforming and combining these two different structures, and you get to another Buchimili automaton. And this is what you need to do. So you need to incorporate this. Remember that in the beginning, when I discussed, you do the intersection with the CCTs, the Buchimili automata do in the opposite direction. Instead of the intersection, take the union. But it's just the correspondent one to do with the Buchimili automata because I think on models and CCTs. So that is intersection, but here in this framework is equivalent to do the union. That's why you do the union. And then you obtain then the final Buchimili automata, which is the knowledge of your new knowledge base after doing that, those modifications. And then you can compute that. There's an example, but you can do this for any automata in any preference relation that's being specified with the Buchimili one. So this is it's for the talk. So basically, the idea is to give an overview in the beginning about the knowledge dynamic and the dimensions of the field. I focus on the AGM framework on the path of taking the AGM framework for non-classical logics. You want to take this is much broader than just the AGM. So here I focus on dispensive compactness to these other logics like temporal logics like LTL. I showed you this novel construction. So you move now to external structures rather than remainders, they are internal structures. And you see that you need to do some changes like a drop in totality and going for mirroring that is more expressive than totality as well. We talk about the uncomputability of this AGM contraction and these more expressive logics, the non-finitary ones. And you showed one strategy you found one class of computable contraction functions in LTL, and for that use Buchimili automata to represent and reason with the knowledge, and Buchimili automata to represent preference relations. And then you can put your final operation, the final knowledge, your body of knowledge. So thank you so much for your attention, and I'll be happy to answer questions if you have.